Thanks for the shout out, Lisa. So I'm gonna do BitVM3 intuitions. Hi, my name is Jose Storopoli. I go with Storopoli, my last name, on Twitter. I work at Alpen Labs, alpenlabs.io. And who here has heard about Garbled Circuits? Who knows how Garbled Circuits work? All right, this is a talk for you. Okay. So first of all, why do we doing this? Why do we using BitVM bridges? Because they have really nice guarantees. They are comprised of a federation, but it's not a majority trust network. It is only a single honest member suffices. So what does that mean? You can have 100 plus cosigners to do a trusted setup. You can have 100 plus operators in the bridge setup, and the guarantees is that it is safe and live. It means that nobody can steal deposits if you have one out of those n cosigners as live and honest, and nobody can stop a valid peg out if you have a single live and honest operator, or yes, operator. What is really nice is that you can become a member, so you don't have to trust anyone. BitVM3, Garbled Circuits, the collateral requirements, it's not that big. And someone, or maybe a group of people, can join together and become an operator, and they don't have to trust nobody but themselves for all activities in and out of the bridge. So, comparison, we had BitVM2. BitVM2 was a really nice breakthrough, but we were doing everything on-chain. So we were verifying SNARK, a zero-knowledge proof, on-chain. So the assert transaction, which is when you are challenged in this optimistic protocol, you have to do an assert transaction that is 2 megabytes, half a block, and then to be finally disproven, someone would have to post a 4 megabyte transaction. So 1.5 blocks of Bitcoin just to prove that someone was a faulty operator. BitVM3 moves that computation off-chain, so you don't need to do big scripts. Now, the assert transaction is just 8 kilobytes, and the disprove transaction, it's pretty much 200 bytes. So you go down from 6 megabytes to 8.2 kilobytes. There's a bunch of variations. There's like different styles of BitVM bridges. There's like different implementations, but this is kind of like the BitVM Alliance 1 that is somewhat canonical right now. Although nobody's building that, it is becoming the canonical bridge. So what is the key idea here? We have something called conditional disclose of secrets. This means that I have a really nice black box that we know that it is trustful black box. It will do what it's supposed to do. I come up with this black box. I give it a snark proof pi here. So okay, this is the proof that I did a bunch of computation, verified computation, and if I feed a false proof to the black box, I leak a secret. And this secret is used to slash my collateral on-chain in an optimistic protocol. So the setup is that we all agree on this black box that is going to leave off-chain. During assertion time, the operator posts, reviews the proof pi on-chain, because we need authenticated inputs, so we use Bitcoin to authenticate inputs. I grab that proof pi from layer 1, from your on-chain transaction, I feed it to the black box. If the proof is correct, I learn nothing. If the proof is incorrect, I learn a secret that I can slash you. This could be like a preimage to a hash lock, for example. That's the main idea. Now, how do we build this black box? We do it with Garbled Circuits. Now, Garbled Circuits, they work on binary gates. And this is a single binary gate. This is the AND gate. You can have like XOR or OR gates and all of those nice little zoo of binary operations that everybody has learned in computer science 101. So here's A and B equals C. Now, these are the binary labels for the gate and the output. So this is kind of like a truth table. So as you can see, A0, B0, A and B, 0 equals 0, 0 and 1 equals 0, and so on. Now, this is a single gate. The key idea here is that you can build any black box, any Turing complete bounded function. You can build it just using binary gates. Now, the idea is that you garble this. So instead of using values, you use labels. A0, B0, C0, and this could be like, I don't know, hashes, or could be something, 20 byte IDs. And what you do is you have an encryption scheme that you encrypt with a key and message, and you get a ciphertext, and it's a symmetric encryption. And using the same key and the ciphertext, you can recover the message. Now, how you do it is really interesting. For example, for you to garble the output of the first row, which is C, 0 from A and B zeros, you pretty much use the key, the labels of A0 and B0. And the message is the label C0. And you do the same for all other rows of the table. And of course, you shuffle those rows because you want to hide information about them. So, and you also make this in a verifiable way. Now, what happens is that once someone is ready to run the Garbled circuit, you just show this label on-chain, and you feed it to the gate, and then you get the correct output. So that's how a single garbling gate, binary gate, works. Now, the idea is that you can compose a lot of those gates, billions of them, into a Garbled circuit. And the input labels review corresponding output labels, and then you can pretty much go and follow through the whole circuit until you get an output in the end. And Isaac verify circuits enables universal computation. This means that we can create an off-chain SNARK verifier that you post the proof on-chain, but the verification is off-chain. And if the proof is false, you get to review the secret. And output label for false is the fraud proof. So if somehow you feed a false proof through this Garbled circuit, it will output a secret that you can slash me on-chain, because that proves that I am a faulty operator or faulty member of the protocol. Now, quick comments on the evolution of BitVM GC schemes. So they are all based on YAO style garbling, which is from YAO in 1986. Good thing is that this thing is 40 years old. In cryptographic terms, this is pretty much like prehistoric. It's really old. So they are really simple. They are really bad because you need 100 gigabytes in circuit size to encode a Graph16, which is one SNARK verifier. And for you to do this, the setup time is 30 minutes. Now, Liam Egan, who used to work at Alpen, he devised something called Glock. And the original paper, Glock, uses another SNARK that is called designated verifier SNARK in a protocol called Perry. And good is because it now reduces a lot to hundreds of megabytes of circuit size, but it is permissionless challenging, and also it used some exotic cryptographic assumptions. So it used as a designated verifier, a not so used SNARK, Perry, and also binary curves, which is kind of like exotic. Now they have a new bridge called Argo. You might have seen Argo Mac, which is one part of the bridge. And there is something that they haven't published yet, which is they are calling the secret sauce. And Argo Mac with the secret sauce creates the Argo bridge. Now they claim, Egan, Liam, and Yingtong, which used to work at the Zcash protocol. and also in the Ethereum Foundation from the ZKID stuff. They claim that it is good. We do have a 32 megabyte circuit size, and you have permissionless challenging, so anyone can challenge. It is not permission. We do have a slightly larger on-chain footprint, and finally we have a new one from Babylon, which is called Babe, and it based on Argomec and linear witness encryption. We did a whiteboarding session yesterday to go over what linear witness encryption means and all the primitives. So it is good because the circuit size, it's also small, 50 megabytes, but the bad thing is that it's permission challenging. So only a verified set of entities can challenge an operator or another member of the protocol. And how it works, so this is a very simple transaction graph. Most bridges, they have something like this. Alpen Labs doesn't have something like this. It is a little bit more complex. But how it works is that somebody deposits 1 BTC here, and this is under the bridge public key, music N of N, UTXO set, and this whole graph is pre-signed. And every operator has its own version that they can span from this graph. Now, suppose I'm an operator and I want to do a withdrawal from the bridge. I go and I do the kickoff transaction. Here I put my pi labels on chain. So here's my proof that I can perform this withdrawal and I can claim that deposit UTXO, that 1 BTC is dutifully mine. Now, what happens is that we have two paths here. Either one that is very happy, optimistic, time-locked for 1 week or 1 day, that I can pretty much withdraw, I can pretty much span this 1 BTC, but this connector here is time-locked, so if nobody challenges me, I get my 1 BTC out. There's another one called disprove, and this one, this connector here has a hash lock. That hash lock is my secret. If you get my pi labels that I posted on the kickoff transaction, not only it enables the withdrawal and disprove paths, but also if you feed this to the Garbled Circuits, and it spills out a pre-image, my secret, because the proof is invalid, then you can slash me right now, no time locks, and you can take the 1 BTC either for yourself or you can burn it. And also, we can add more collateral here, so if I get slashed or disproven, I also lose a lot of money. So that's how BitVM3 works in a nutshell in intuitions, and I think we have a bunch of times for questions as well.
Thank you, Jose. I see that you're talking about like covenants usage to make sure that I believe it's going to be like a check template verify kind of thing here.
Yeah.
How is that done without a covenant?
How that is done without what?
Without covenants.
Well, I mean, that's a really good idea for a research paper, but I do think that all covenants can be emulated with connector outputs and pre-signed transactions.
Okay, so connector outputs. Okay.
Yeah. All of those things, they are connector outputs. All of those 0 BTCs, BTCs, they are connector outputs. So I think that most people here don't know connector outputs. Who here knows what covenant means? All right, transaction introspection. So if I want this 1 BTC to go from either one of those flows and not be spent by anyone, only through this way here, what I need to do first is I need to do an interactive session that we pre-sign using N of N music tool, that we pre-sign this graph for every operator. Now, this is how we enforce that all of the deposits will follow this template. Unfortunately, CTV does not help us here because we need to change the inputs depending on the operator. So
you need any prove out?
No, I think transaction hash can work.
Transaction hash can
work. Yeah, because we choose which parts of the transaction we want to do it in the template, in the covenant.
Okay, thank you.
I think you can do with CTV, but then you do that bear script hack, which I think doesn't work anymore, and it's gonna annoy a lot of people if you do that. Yeah. But I don't know much details about that.
No, I don't know the details either, but if people want CTV specifically for the bear script hack, that sounds like a very bad reason for it, and we should just design something that does that is designed to do what people want to do with it.
Yeah.
Anyway.
Also, have you seen the Bino hash?
The who hash?
Bino hash.
I have not.
All right. You are gonna have so much fun when you see how it works.
Okay. How does it work?
Okay, so I haven't read the paper because this was published right when I was at the gate, flying here at the airport. So it does a very weak introspection covenant that we can use for BitVM style bridges. But the way it works is that it uses a binomial search. It's binomial search. It is search and delete, opcode search and delete for multisig, but it uses in the locking script and also deals with 256 different sig hashes and all bear script transactions. And first of all, they are non-standard, and also you need to patch your node to mine them.
So we're going to have a bunch of drama soon for another standardness rule change.
Yeah, and don't quote me on that, but one of the intentions surrounding those things is to show that we can do covenants. Right now, it's going to be ugly. It's going to be really ugly, and we should.
I like these arguments from fatalism, sort of as an approach, right? So you say, this is terrible, but it works, and we're going to do it, and you'd better
I'm not saying
do the
that.
soft fork. No, you're not saying that,
Yeah.
but like one could say that.
Yeah.
Yeah, it's a strategy that's out there.
Yeah.
It's kind of also a way to remove people's concerns, because one of the fears with covenants is like, oh, what if we get MEV, etc. And if you just say, well, it's a fait accompli, it can already be done, just embrace it, it just diffuses that concern.
Yeah, one can say that.
Which I guess all of BitVM is kind of a way to say that.
Yeah, I mean, BitVM is a really big, clever, unelegant hack to do covenants and verify computation on Bitcoin.
Yeah.
The whole thing is unelegant, but some parts within that unelegancy, they are elegant.
But I mean, here you're saying this particular tool could be made better with a simple covenant like TX hash or whatever.
Yeah.
But are you saying ultimately you don't need BitVM at all if you have even more powerful covenants, right? Or
no, because what BitVM allows is for you to verify a snark optimistically on Bitcoin.
We need a
if you
snark
had
opcode.
256-bit arithmetic or even 64-bit arithmetic in opcodes, I think you can do it without being optimistic in a sovereign, trustless way.
Or even just a snark verification opcode would remove all of BitVM.
Yeah, but then we are pretty much kicking the can down the road, because we're going to have a discussion in 5-10 years that, yes, we're still stuck with that old snark and we need to upgrade to a new snark and we need a new soft fork, new opcode. So having the primitives of doing whatever verification you want with ideally 256-bit operations or 64-bit operations is already a very good thing.
But how big would these be? If you just have these arbitrarily large arithmetic, do you still need like megabyte scripts, or is it kilobytes? Or
it can be, I think, under, if you have 256, don't quote me on that, but I think maybe under a kilobyte, probably. If you have 64
but then the argument would be there's a bunch of these kilobyte scripts on the chain. If we had a dedicated snark verification opcode, you would make it smaller.
Yeah.
But then probably it would be computationally expensive, and so it would have to count as like more weight than a number of bytes, or maybe might not even be useful to have an opcode then, if the opcode has to be very expensive, right? Because We have things like script checks, and they're limited, right? You cannot fill the whole block with check 6. So you might end up with something similar where the snark code cannot be there. Like, you can't just fill the whole block with snark verifiers. And then you might as well just use the low-level script, and you can build any snark verifier you want.
Yes, you can do that.
For the same cost, eventually. Even if it takes more bytes, there's a limit, there's a constraint on the block, so you can't do more than that anyway.
Yes, and you can also, I don't know how more expensive they are compared to checking signatures. For example, a Raspberry Pi or a very low-end device, it can verify a lot of those zero-knowledge proofs. And also hardware is scaling in a very nice positive trend. So even very low chip devices, they can do batches of those zero knowledge proofs. You can also do something that...
You can benchmark it against signature checks. That's probably the most relevant metric to compare it to. Yeah.
You can do that. I'm not sure if someone has done that, but you can do that. There was some recent work by Conduition on doing some benchmarkings around hash signatures again versus Schnorr signature verifications. Someone could do the same with zero knowledge proofs. Thank you for the question.
José, I had like intuition about what you said, like the whole presentation was pretty good, but I want to know like how would that work on Alpen with like you have like operators, you have members. I still don't quite get the figure of like what is the whole role on each one of them. And like, for example, you said like some of them I could like verify them myself and it's permissionless. Would that mean that like I would run like an Alpen node on my computer and then try to verify or make proofs? Like how would that work?
So at Alpen, we are running a permission bridge, but you can always run a node and verify everything. You can always run a full node and verify everything. We do have full nodes. Alpen, the transaction graph is a little bit different. At Alpen, we have what we call the Linus bridge. This is the Linus bridge. And also, we have an alternate design that will be shared soon by Christian Leve that works with us. And we call that the Leve bridge. So the Leve bridge is a little bit different. The responsibilities are different. Who has to post things on chain. And also, I do think this is not defined yet, but I do think that we are going with a mix of, I mean, several people call this different. Some calls like operators and signers, some calls operators and watchtowers. The idea is that operator, they process the withdrawals and they have some collateral tied to the BitVM transaction graphs. And signers or watchtowers, they don't process withdrawals, they don't have collateral tied, but they are an extra liveness assumption and they are in the permission set that can challenge faulty operators.
Okay. Thank you.
Any more questions?
Also, one, since we touched into Alpen specifics, if you go to the Glock paper, Garbled Lock, it is using the dv-parry designated verifier snark in a binary curve, and it's very small. It is currently this word smallest snark. It's the proof size. It's even small than Graph 16. But our Glock bridge that we are launching mainnet this year is not based on dv-parry, it's based on Graph 16. So it's a Graph 16 snark. So Graph 16 is a constant size, one of the most non-designated verify, so everyone can verify the proof, is the world's currently smallest proof size, around 190 to 200 bytes. And the vParry, I think it's 120, 130. But it's designated verify, is also constant size, and it is the world's smallest snark. No other zero-knowledge application has a snark that has a smaller proof size than the vParry, which is the one from the Glock paper.
You were saying like if no one else has questions, I'm just gonna like keep asking them. But like you said, right now BitVM Alliance is going towards a canonical state of BitVM. But
okay, let's talk about BitVM Alliance politics. So
yeah, what is BitVM Alliance?
Yes, BitVM Alliance. It is an alliance. I think we have several members of the alliance. Most notably, I think the ones that are, this is not Alpen's opinion, this is my opinion. The ones that are serious, I think it's Alpen, Citria, and Babylon. I think we do also have other members, but they have like their own tokens and so on. So you take any conclusion out of that. And we also have other players that revolve around the alliance. They're not members, like Fargate Labs. They're doing a lot of stuff with BitVMX and so on. And the BitVM Alliance, it's not only coding BitVM bridge primitives and canonical protocols, but also auditing those protocols in a shared pool of resources. Everyone kind of like donates to the alliance to audit those things. Zalek just audited the BitVM2 bridge, but recently it's starting to like do some forks and some splits off. So Citria is using kind of like, they use some primitives from the BitVM Alliance bridge, but their bridge is not the same as the one that's BitVM Alliance. We also use some primitives from the Alliance, but our bridge is different than Citria. Babylon is doing their own thing as well. So that's the whole state of the BitVM Alliance.
Okay, thank you.
Any more questions? We have plenty of time to more discussions.
There's also a recent company that was founded by Robin Linus, Ying Tong, and Liam Egan, which is called IDEO. And they are aiming to build a bridge, which is the Argo bridge, because they pretty much are the ones, two of the three co-founders, they are the authors of the Argo bridge. And the Argo bridge, they are going to do a bridge only for a shielded CSV side system, which is a shielded client-side validation, which is a paper that Liam Egan and Robin Linus published in 2024, I think, which is for very private and minimal on-chain footprint payments, very focusing on payments.
Is there any like very clear advantages that like the Glock setup would have over an Argo-based setup, like assuming that you built or you had like equal time and resources to build each?
So Glock was done in 2025 and maybe mid-2025, I think. And Babe was just announced 2 or 3 weeks ago. These things are really moving fast. So right now, there is also some research in Alpen that will even improve upon Babe. The problem is that those things keep increasing, advancing, and getting better, and so on, more efficient. At one point, you have to say, okay, let's freeze this whole thing and let's go with this design, because you need to build a lot of engineering stuff, a lot of tooling, a lot of clients, a whole ecosystem around it. And you also need to audit, you also need to go after the partnership. So we are launching with a Glock design focused on Graph 16, not on the vParry. And probably we'll do a bunch of updates that will make the bridge more efficient, moving towards something like Babe or Argo and so on. But right now we are locked for mainnet this year with Glock and Graph 16.
I guess related follow-up question is, like how many more variables are there to optimize? Like it seems like all of the big costs have virtually gone to zero, including like on-chain footprint, off-chain data, like computation.
I mean, a lot of the things they pretty much depending on how many breakthroughs we have in cryptography, in like cutting edge cryptography. I mean, yesterday we discussed linear witness encryption. So if someone can come up with a way to do graph 16 in a witness encryption setup, then pretty much you don't need a BitVM bridge. You can do this with a very simple transaction graph, and it's pessimistic, non-iterative, instead of being iterative and optimistic. Pipes also have done that, but their ciphertext from the witness encryption is 338 terabytes. So yeah, but it's pessimistic and it's non-interactive. But the ciphertext that you need to communicate off-chain is 338 terabytes. And there's snark. It's recently published, so it's a new snark that's based on affine transformations, something like this. I don't know how. They don't have like a proof, a really good reduction proof that the scheme is secure. They have like some proof of correctness under certain assumptions. I can say you that the lower bound is the size of the graph 16, maybe 200 bytes, and no interactive. But we need to. Also, you heard about Pipes V1, which uses functional encryption and indistinguishable obfuscation, I/O, which is not feasible yet. I don't know if it will be feasible, but theoretically it's possible.
Okay.
Depends on a lot of things.
Yeah.
Question about permission challenging. What I heard, rumors or opinions, is that generally you would say permission challenging is bad because permission bad, but because you have this one of n set up anyway, it's fine as long as the permission is one of n. But then, if I understand that correctly, then it's still bad in the long term because as soon as you have a covenant opcode, as soon as you have something like TX hash, then you can have 0 of n. Or does that not actually solve the permission, the one of n problem? No, I guess not, right? There's a separate problem. You want covenants to get rid of the pre-signing, but if you want actual permissionless challenging,
I think
need
that
something
covenants might get you permissions challenging.
a different kind of covenant, so more than TX hash, or
I don't know. I need to get some days off and work on that. But I don't know. I think that they could. They could. I would be surprised if, I don't know, maybe I'm making a fool of myself, but I think that you can get permissionless challenging if you have some sort of strong covenants here.
yeah. But I guess my follow-up question is, if I look at the two last lines, Argo versus Babe, given the criteria you're giving, it looks strictly worse. It's a bigger circuit and it needs permission, but I'm sure the authors like it. So what?
Well, how it works is that Babylon bought early access to ArgoMac. And so they went ahead and already published Babe. But Argo, it's a bridge that the second part of the bridge, the ArgoMac something, equals Argo, is not published yet. So yes, Babe is slightly worse than Argo, but once Argo goes public, maybe Babylon or Alpen or Citria can do further optimizations.
Oh, that's what the secret sauce is.
Yes, the secret sauce has not been published yet. No,
Okay,
the
so
secret sauce.
Argo has the secret sauce, and that's how they get 32 megabytes. Babe does not have the secret sauce.
Yes.
Okay.
And we don't know what secret sauce is
Magic.
yet. What?
Magic.
Yes, or you can pretty much buy early access as well, if you want to know early.
No.
Yeah.
was thinking, like in a versatility scenario, what are the attack surface on this? Sorry?
There's a talk about?
Oh, is there attack?
Yeah, but they are like, I think, attacks on different bridges.
Yeah, so there's going to be a talk about historic bridge hacks across the
historic.
crypto ecosystem.
So, first of all, the canonical ones, you could have a bug and so on, but most of the, so how it works in a roll-up style side system, it means that when you post a proof and you want to spend a deposit from the UTXO as an operator, from the bridge UTXO set to yourself, you post three things. First, you post that you were assigned to fulfill a withdrawal in the side system, or in a checkpoint to the L1, and it's in the canonical Bitcoin chain. Otherwise, you can run your private fork and say, hey, I have a transaction here, and see, I was assigned it. So you post that there is like a signed checkpoint from the rollup sequencer that you were assigned to fulfill a withdrawal. Second thing that you do is that you fronted the user the withdrawal on L1, on the canonical Bitcoin chain. And what was the third thing? I think those are the major two things. And the third thing is that all of this happened in the canonical Bitcoin L1. Yes. So once you have those things, you construct a graph16 proof for those things. And that's how you spend a withdrawal to yourself from the BitVM UTXO bridge set.
Thank you.
Cool. Thank you, Jose. A big round of applause for that.